Hello. So now I am going to say that how to do a routine cyclic voltammetry and what are the parameters need to be considered before cyclic voltammetry. First of all, that I want to make sure that my instrument works or not. So what I do is just I close the software. Here, this is the icon. I am trying to open that. I say that run. It's fine. And then I want to make sure that software is communicating with the computer. The computer and instrument handshake is being done. It says everything is okay. I could see hardware is healthy. I say okay. Yeah. Now I am sure that my instrument is communicating with the software. So I am preparing a standard solution. So I am taking some potassium ferricyanide crystals. So that can you see the crystals? So few of the crystals. I am taking that 2 crystals. So basically I have to prepare a 1 millimolar solution. So I am taking the 2 crystals from the bottle. And I am wearing that 100 millimolars. So basically that from a spatula, I take that what you call 2 spatulas, so that I do not weigh that the supporting electrolyte. So since it is not that costly, and I do not to be precise in that what you call concentrations. So I prepared a solution. So I dissolved it properly in a 10 ml solution. I filled it. So later that I want to make sure that how my electrodes are. So I could see that working electrode and a reference and counter. I am inserting it. So I am ensuring that all the 3 electrodes are dipped and there is no air bubble anywhere. So I am giving the connections, that green for the working and white for the reference and red for the counter. Now the physical connections are through. So in the salt, in my sample, I added a salt to increase the conductivity. Sometimes the dielectric constant of the solvent will play a role. So since water has a dielectric constant near around that 80, see any ions what we put, right, that salt will be separated by. So that basically that any solvent there will be some resistance. To decrease the resistance, we added a supporting electrolyte. For water, I added a KCl. In case of organic solvent, like dichloromethane, acetonitrile, or DMF, we will be adding that tetrabutyl ammonium perchlorate, TBAP. Either the tetrabutyl ammonium perchlorate or tetrabutyl ammonium PFC. Anything will do for us. That salt should be soluble in the solvent what we use. So KCl we will be using it for water, and the tetrabutyl ammonium salts we will be using it for organic solvents. Okay. So water and okay, I put a potassium ferricyanide. I know that why I am using that particular sample. Potassium ferrocyanide and ferricyanide, both are available in the bottles. That means that both the oxidation states are very stable. Now what to start? So I am clicking on the technique, using cyclic voltammetry. I say OK. Then I come to the parameters. This is all 0, 0, 0, 0. So now what to enter here? So I assume that I do not have any idea that where the potassium ferricyanide peaks are. So I start with the 0. I put the high limit as a solvent limit. So for water, oxidation will happen at 1 volt. I am giving that a 1 volt as the high limit. Low, I am giving that water reduction limit of -1 volt. And final 0. So that between that, so I am asking the software, go from 0 to 1 volt, come back to -1 volt and to 0. So initial scan polarity, I say that positive or negative. What does it mean? So here I have taken the potassium ferri. I have to reduce it to the Fu2 plus. So that actually I have to go towards a negative direction. I'm not sure that what I'm choosing is right or not. I'm using my common sense to fix the things. So scan rate, I say that I do not want to go to higher scan rate. I say 50 millivolt per second. So 0.05 volt is at 50 millivolt. Sieve segments. So 0 to 1 is one segment. 0 to 1 plus 1 to minus 1 is another segment. And coming back to 0 is the third segment. So I have to use segment of 3. And I will say that enable the finally. So it will stay at 0. Scan data I had chosen, sieve segment I had chosen, sample interval I am giving default. Quiet time 2 minutes, so it start the measurement after 2 seconds. So that's fine for me, I am not doing that. Now I have to guess a current. So 1 into 10 power minus 6 is 1 microampere, and 10 power minus 9 is at nanoampere, and it's a milliampere. So for 1 millimolar, normally I expect that for this electrode surface, I expect between the 10 power minus 5 and 10 power minus 6. So yeah, I'm not sure, still I'm choosing that 10 power minus 5, it's a 10 microamperes. I'm saying that auto sensitivity, that what is happened, that I'm choosing it. That's why. Now I'm not sure that this is correct or not. This is a guess I'm making it. I say OK and run. It obeys our command. It's starting from the 0, go to that minus voltages. It seems to be that what you call that dissolved oxygen peak. I have not degassed the solvent, so I am getting that what you call that the oxygen peak. Now the thing is that so that this seems to be that water started. I expected around minus 1 volt. So I could see that water reduction starts around that minus 0.9 volts. And so this is a small that what do you call the dissolved oxygen peak. If I purge it, that this peak has to varies. So now where is that what do you call that sample peak? So sample peaks, I think that it seems to be that my sample peak. So potassium ferricyanide that Fe3 plus. So right now I think it is in Fe2 plus, becoming Fe3 plus. It's coming back. So probably that I have chosen a starting potential very wrongly. So in first CV it tells me that I have not chosen the correct starting potential. So let us see that. Let us analyze, then let us try to improve on the CV. So the first guess would be that first we have to scan between that solvent limits. In the solvent limit we have to choose the right one. So this is the way that whatever we measured, the CV we got it. So basically that I do not want to scan the second set of experiment. I do not want to scan beyond that what you call that minus 0.9. That is true. And Fe3 plus to 2 plus. So I have to the redox couple happens near around that 0.2. So since I am starting with the plus 0.3. So that since my redox potential is around that what you call that plus 0.2, I start from that somewhere here. So the thing is that so my Fe3 plus will be reduced. So this will be that the second CV. I'm not saving this one because this gives me an idea that what I have to do in the next one. So I start from here, then I will do the measurement. So the thing is that I'm trying to improving the things. So initial potential I start from 0.5. Why? Because I want to reduce it Fe3 plus to Fe2 plus. And high is 1 volt, I'm happy. Low minus 1 volt. Instead of that, I say minus 0.9. So that is the feedback I got from the previous CV. So then come back to the again that 0.5. So and I could see that the current I can go to microamperes. So that's another improvement I'm making. OK and run. So you will get bored in between. So that's why we are making a noise of tick 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 kind of things. So that you will hear something always in the background. You see that oxygen peak again, it comes. And it's not always to scan that, what you call that, things that which we do not need it. So either I have to degas it or I should not scan that things, that negative area where I do not expect any peaks. Good CV, very good. So here that Fe3 plus got reduced to Fe2 plus. I am oxidizing it back to Fe3 plus. Yeah, it's obeying our command. Now third segment is being scanned. So we told them to stop at plus 0.5 volt. Software obeys our command. Let us see that is there any improvement compared to that old one. I think that this is somewhat more informative. So basically now I do not want to scan that. Okay, since I know that it is coming from that water reduced oxygen, I will not scan this one. So now this time that I will scan only this region, plus 0.5 to minus 0.1 will do for me. So that is a third CV. What I will do is I start from plus 0.5, I am happy. Highest one I am happy. Low, since I am not, what you call, purging the things, and I do not have any peaks beyond that, oxygen peak. I am not scanning it. Finally, so stage treatment 2 is sufficient for me now. I am saying that go to 0.5, starting from 0.5, and then there is no need to come back again to this one. So 0.5 is sufficient. High again, keeping that 0.5. So you start from 0.5, go back and come back. That instead of that, I will start from 0.6. So that 0.6, high is 0.6. Okay. Yeah. Now I am improving upon my scan range, so that I do not want to record all these unwanted peaks. Sometimes that it may contaminate my electrode surface. So this time I will scan only the things where I expect my sample peaks. I am starting from plus 0.6 and going up to that minus 0.1, coming back to 0.6. Sieve signals I am making it to 2. Current is 1 microampere. Auto sensitivity, I think that I will be getting a good CV. I say OK. Done. So software is obeying my commands, starting from plus 0.6 and starting from the positive side. Why? Because I wanted to reduce Fe3 plus to Fe2 plus. So that the Fe3 plus reduction started here, and I could see that what is happened, that the peak gone up to that, and now that Fe3 plus is being converted back to Fe2 plus. I'm getting a nice looking CV. Click on the data plate. So I am looking at I exactly that. Now I recorded the peak of my sample. So now what I expect, so that peak difference, it's near around that 0.11 and 0.23. So it's near around that 120 millivolt is the difference. 120 millivolt is not acceptable to me or anyone. So I wanted to improve. So I will make it 2 improvements. So first I will add a little bit of more supporting electrolyte. I am not getting a small spatula over here. So is it case here?
Yes.
Okay. Let me try to add some more case here. So I anticipate that there is a insufficient supporting electrolyte. So I have to make 1:100. Sometimes when you do not weigh that, you will have this kind of problems. So simply that I will try to add something. So I do not add a stirring facility here. I stain myself, or I can use what you call basically, yes, this produce medicinal peaks. That's glass rod. I use a glass rod. This is good enough to stir the solutions. Good. So that I'm ensuring that the KCl is getting dissolved. So there is no, it leaves that no crystals behind. So that way that I'm sure that KCl is soluble in water, so it dissolves faster. Now I'm trying to put my solutions back. Everything is fine. If there is an improvement, I wanted to see is there any improvement. So now I wanted to save this one. So I'm going for a document. Can I make a folder here? New folder. Make a folder here. New folder. New folder name. I put the CV. I say that. CV1. Okay. Okay, efficiency. CV6. Okay. That is fine. I'm saving it. Now I'm not changing anything. The same parameters. I'm running it. Then let me overlay that. Let us see that the change in the supporting electrolyte, addition of supporting electrolyte, has any impact in the CV. So far so good. Now it's fine. I'm getting the peak. I'm not sure again it is a 120 millivolt difference or any improvement. Clicking on the things and saving as instead of CV1 I say that it's CV2. Okay. Software accepted it. Now I try to overlay graphics, new overlay plots. So CV2 is there on the screen. I'm choosing CV1. I say open. Is there any difference? There is some improvement. That thing is at CO2. So you see that that peak of that what you call that 0.11 that come down to 0.15. That's a 40 millivolt difference. So just I say that click on the data plot. So 0.13 and 0.24. Now it came down to, the difference came down to 90 millivolt. So previously it was around that 130 millivolt, now it came down to 90 millivolt. So one place we are around 100 millivolt now. So that's a difference of 40 millivolt. I will see how I can able to improve further. Now the thing is that now I am concentrating on the electrode surface. You can give a good tissue paper to me. You can bring one more tissue paper. The contamination is there, so I do not want to use it anymore. Okay. Now I'm using a soft tissues, so whenever we touch that we could feel that softness. And basically that I'm ensuring that hard tissues will not affect the electrode surface. It's not making any scratches at the surface. The surface will be that as smooth as possible. Now I have to, I'm ensuring that what has happened, there is no dirt on it. Okay, so far so good. It seems to be that I have to see my face, it's glittering, and I have to wash with the distilled water. So I use some distilled water to clean it. clean the electrode and I basically I rubbed the surface with the tissue paper. It's a simple cleaning method. And I have saved this one also. Now I am running away to see that any possible improvement. So I have to get a 59 millivolt theoretically, but even if I get that 60 to 70, I will be happy with that. Is it sharp enough? Previously it was around 0.11, now it is somewhere around. I think that it seems to be a good improvement this time. I am not sure. Now I'm saving this going for a data plot to see that there is any improvement. So now it comes to 0.15 and 0.23, so near around 80 millivolt. So I should be happy with the 70 millivolt. That little bit I am far off. See that how that initial CV was, how we improved upon. So basically that we have to, we should not scan the regions that where we are not expecting that the metal oxidation will take place, that for example oxidation results, and because that will contaminate the electrode surface. So first of all we have to scan the entire solvent page, then we have to come to that our sample, so where the oxidation doesn't happen. So we can, for a new sample we cannot able to predict the potential range. One has to do a hit and try, then we have to choose that right page where we are expecting, then do the measurements. Now see, for example, water we have done the set the parameters like that, and what is the parameters to be set for the organic solvents. I would like to use a board now. See, now let us analyze the various solvent windows. So if it is at what you call that, see, let us say that it's a 0 volt and minus 1 volt, minus 2 volt, minus 3 volt, plus 12. If you take acetonitrile, so that goes from that plus 0.2 to minus 0.2. If someone has a peak either in what you call that negative and positive side, so one has to choose the acetonitrile. And in case that it's slightly polar solvent, although not like water, it's a slightly polar solvent. And dichloro DCM has at what you call that, somewhere around that what you call that minus 1.8 to plus 1.8 volt. So I had seen that, yeah, I mean, when it's pure and properly distilled, has a slightly better window than that. And if someone has that what you call peaks the negative side, DMF is ideal choice. So this is a DCM, you call it dichloromethane, or DMF, that is it, plus 1 volt to minus 3 volt. So the thing is that if somebody has some peaks in the negative side, that they have to prefer that DMF and make sure that solvent has no effect on your samples. And when it comes to supporting electrolyte, it's a tetraethyl ammonium perchlorate or tetrabutyl ammonium perchlorate or tetraethyl ammonium PF6 or tetrabutyl ammonium PF6 are soluble in that organic solvents. So in water we added a KCl. In organic solvent you have to add any of your what do you call that, supporting electrolytes. And I think most of them are available in the Aldrich and Sigma catalogs. So otherwise you can purchase a tetrabutyl ammonium chloride and add a perchloric acid, and you take a precipitate and wash it thoroughly, that 5 to 6 times with the water. Whatever that unreacted perchloric acid, you remove it. Then dry it, you can also get it. And sometimes there's some export restrictions for the perchlorate salts. Such cases you can purchase a chlorate salt and you can convert yourself. Okay. Now, say, assume that what is certain cases, there is what you call that, we get a peak, well-defined peaks that software will automatically calculates the peak height, current height, area kind of things. For a sample that sometimes the broad peaks you cannot able to do that. Such cases what you do is, you say that, well, this is manual result. I click once again, I get the arrow mark. I put a tangent properly. Then the thing is that software will calculate that what is the current height. So current height is at your IP. That EP is the potential, and this is the area. So software calculates automatically. We have to make a right tangent. So whenever the peaks are not well defined, please you can do that. Okay.